And Blair, of course, is the CTO of Neuton.ai. He's a results-focused leader with a demonstrated record of delivering profitable global scale outsourcing and professional services to Fortune 500 companies. He has more than 20 years of experience, and he actually led quite a few companies in the past, such as T-Systems and Bell division of Deutsche Telekom company, actually. So Blair will talk about avoiding loss of quality. Blair, if you can share. Oh, something is coming up, but I don't see. Oh, there it is. Avoiding loss of quality while in pursuit of a tinyML model. But I think the focus of this talk, as he had said earlier, and pretty sure a lot of people are waiting to hear, it's about explainability, and which is what, from what I see in the slide, the next chapter of her tinyML. Let me take the opportunity to thank Blair and also to state that there will be a Q&A session for Blair's talk, and also for any other issues that were shown earlier in the keynote. So please take advantage of the session and Blair's availability if you have any questions at the end. So Blair?
Again, for the introduction, and thanks again to everyone who's taken the time out to give us an opportunity to introduce you to Neuton. Neuton, just in summary, is our zero code AutoML solution that we've really designed for not only the non-data scientists, but also for the data scientists alike. And just to kind of summarize some of the things that we discussed earlier in our session during the keynote, is that our objective when it comes to delivering a solution, especially around tinyML, it really falls into a couple of different categories. Number one, we're looking to enable machine learning or tinyML to everyone. When we begin to think about how we can accomplish some of the goals that were defined with the tinyML organization, when we said, hey, we want millions, if not billions, of intelligent devices in the ecosystem, how do we accomplish this? And one of the areas where we're playing our part to help accomplish the proliferation of tinyML is by making machine learning available to everyone. And we mean that in a very real sense. So that's the first area. Number two, the ongoing problem that everyone has been continuing to look to solve is how can I now integrate my models into devices or into microcontrollers. And earlier we kind of explained that we're taking a completely new, I would say, disruptive and innovative approach to building models. So we're not following, I would say, the traditional approach where you start out with an existing network structure, and then from there you apply different techniques to compress your models, such as distillation, quantization, et cetera. We take a completely different approach. We actually build each model per use case, neuron by neuron, not compromising accuracy along the way. But then once you're able to actually successfully implement your model into your ecosystem or for your given use case, then it comes the next important question. What is your model quality? What's driving your individual predictions? And for today, we're going to talk, or for this particular session, we're going to talk about explainability and the importance around explainability. And we begin to define explainability really into 4 very distinctive steps. And these are the questions that, again, I ask all of you guys to ask yourself. When you reach that point of implementing your solution, you want to ask yourself, what does your data consist of? Do you have these insights today? Number 2, what are the most important features that are driving your predictions? Or maybe even to some degree, understanding what features are not influencing your predictions. Next is understanding why your model makes certain predictions. And then lastly, when should you actually reconsider, or when you should consider retraining your model? And these are the 4 areas, these are the 4 tools as it relates to our explainability office that I will go over today. And today's discussion, or this particular session, I'll go through a couple of different slides just briefly, and then I'll show the platform live so that you can see it in action. So starting with, just in summary, the what. The first tool in our explainability office is our exploratory data analysis tool. It gives you insights as to what your data consists of before you begin training. And we'll show this in just a moment so that you can have, or you can see, you can have a significant amount of insight as to what your data consists of, whether it is just the overview of your data, whether it's looking to understand the binary correlation of some of your features as it relates to your target variable, looking to identify any potential outliers that may exist in your data set. And then where, I like to say where are the most important features in your data set? And important can mean a couple of different things. Number one, importance as to which features are actually influencing your predictions significantly. And also the latter, or the other side, which features are not influencing your data set. So we give you insight into understanding both. And then the why, which is one of my favorite tools, is being able to understand why your model is making certain predictions. And not only being able to understand why your model is making certain predictions, but also being able to have the insight to understand how each feature is actually influencing your predictions. And we allow for you to do this dynamically, and I'll show you that in just a moment. And then the when. Of course, going through the process of actually developing a model, integrating that model is, of course, it's essential, it's important. But what's also equally important is being able to have the foresight to know when the model that you've created is no longer doing the job that you expected. And that's our next tool in our explainability office, which is the model to data relevance indicator, which gives you insight. It gives you a forward-looking view to understand when your model may be decaying and when you may need to retrain your model. So we'll show that as well. And in our example, we've taken the opportunity to use a use case or data set that maybe most of you are familiar with. It is a data set around being able to predict the quality of benzene in the air, which can be harmful. So this is a data set that we've taken an opportunity to already train. But more importantly, I just want to highlight that it's a regression problem. So we'll be able to have some insight there. And we've also included a link as to where you can access the data set. And in this particular case, the target metric that we're using, based upon the use case that was put out, not by ourselves, but on this particular site, we'll be using the target metric of mean absolute error. Now, if you're like me, I'm not necessarily an expert in this particular area, so I just want to kind of highlight a number of the different terms that you may see within the data set, just so that we can have some baseline and some alignment, especially when we get into the model interpreter and begin to change some of the variables so we can see how it influences our target variable along the way. So I'll just spend a second here and I'll begin to kind of transition over to our platform. So hopefully everyone is able to see our platform at the moment. You should see your workspace is a tile-based workspace. And I just want to take a moment to highlight a couple of things that I discussed during our earlier keynote discussion, is that our platform is designed not only to enable the non-data scientists, but more importantly, we've streamlined our workflow into 3 very simple steps. The first step, just as an overview, is that you upload your data, you identify your target variable. In this particular case, as you may recall, it is, we're looking to predict the average amount of benzene concentration in the air. This is, of course, there are sensors that are laid out in various locations that they're looking to get some real-time readings on. So this is the first step. You upload your data, you identify your target variable. And then the second step in our workflow is training. And of course, since we're looking to focus on our explainability office, the training has already been complete. As you can see, just giving a quick overview, it took us 20 minutes to train this particular data set. Here's our target metric. Here's the problem type, as well as the variable, as well as our target variable. And then additionally, you can begin to look at, even though we've selected a specific target variable, in this particular case, mean absolute error, we report on all of the various target metrics that are available to you. So even though you didn't, as an example, select root mean squared error, we still will report on that and give you some insight. Additionally, just so you kind of understand, wherever you see the arrow going down, that means you're looking for a measurement that is as low as possible. And when you see that the arrow is going up, then we're looking for a metric to be as high as possible. This graph gives you the overall quality of the model, in this particular case, 99%. But also, since this is a forum about tinyML, I also want to highlight to you the number of coefficients that this particular model has, as well as the size of the model. So again, our approach is that we build fast, we build once, and we don't compromise on accuracy along the way. And I think this example also demonstrates that. Then you head into the prediction tab. And from here, I'll begin to kind of give you an overview now, a little bit more in detail about the explainability office that we make available to everyone. So you can, at this point, go into our analytics tools, but I'll start over here into the data set, into the training section. Go to our analytics tools, and I'll start first with the exploratory data analysis tool. So this is the first tool that I'll introduce to you as it relates to our explainability office. So starting first with just kind of understanding the overall, your data overview. Here you can see the problem type once again. You can see the amount of rows, the amount of columns, and of course the size. If there were any missing records. Our platform, we automate everything around data preprocessing when it's available or when it's necessary. And the same thing from a feature engineering perspective. So we automate everything along the way. So starting first, you can begin to look at the different information for each of your features and its relation to the target variable. Of course, you'll find that some particular features are a little bit more informative than others, but nonetheless, we provide the associated information so that you can begin to interpret and understand your data, at least what your data looks like before we begin training. And you can begin to see here in this particular case, this is basically your CO concentration. And you can see that it's fairly linear tracking to your target variable, but you can click through and you can see how the top 10 features, which we've identified, and how all of these various features are relating to your target variable. So you can easily go through. So it's a very rich tool set. And then if we continue to scroll down, you can see that here's a violin plot because this is a regression problem. And we've also began to identify any outliers that you might have in your data. Once again, this is the pre-training view. We've identified those outliers. Once we've identified those outliers, we'll exclude them when we begin the training process so that you're not compromising, again, the accuracy of your model. One of my favorite graphs to look at is the heat map. Here you can see which features have the highest binary correlation to your target variable. And what you're looking for here is one of the things that you look to identify is if there are any features that are have a direct correlation to your target variable, which in this particular case, we might call, it may be experiencing some leakage, which means there's a one-to-one or pretty close one-to-one relationship between this particular feature and your target variable. So this, as an example, could be a feature that you may identify that the correlation between the feature as well as your target variable is probably too high. So in this particular case, and then you can also begin to identify if any two features have a fairly high correlation, which is then telling you or informing you that both of those particular features is providing your model close to the same information. That also, again, may influence your predictions. So you can see here that P208 as an example, S2, P208, S1 in this particular case has a fairly high correlation. But you can also see that P208, S2 has a fairly high correlation to the target variable as well, which may also represent some leakage in your data set. Here's another view that you can take or you can have as it relates to, once again, identifying the outliers in your data set. And there's a number of different graphs that you can go through and identify. And you can see that the magenta are the outliers and the green are not the outliers. So let's scroll up here. Once again, I'll close this out. Then we'll head into our next tool, which is our feature importance matrix, where we're looking to identify, again, which features are having an influence on your predictions. And as I mentioned, we'll list out the top 10 if it's appropriate. So which features are the top 10 features that are influencing your predictions? And then if you like, which can also be equally as important, is understanding which features are not influencing your predictions at all. So of course, if you have a larger data set, or if we had a larger data set, let's say where there was 30 or 40 different features, we'll give you the top 10. And we'll then also give you the bottom 10 that you can take a look at. You can also export this as well if you so choose. Now, we'll head over to the prediction tab. And as we head over to the prediction tab, just as a matter of just summary and clarity, normally once training is completed, we would come here and we'll click enable predictions. In this particular case, I've already done that. And I've already prepared some predictions. I already ran some predictions just to help facilitate the discussion. And so I'm gonna click on some predictions that we've already ran. And now introduce you to one of the tools that quite personally, I'm extremely excited about. And this particular tool is called our model interpreter. As you can see, we ran a number of different predictions, in this case, via the web. And what you can do, what we allow for our customers to do, or our partners, is they can go to each individual prediction. And when they go to each individual prediction, you can now drill down into this individual prediction and understand how each individual feature, specifically the top 10 features, are influencing that given prediction. And we allow for you to dynamically change the value of those features so that you can see how it influences that given prediction. So let's just go here. I'll click on model interpreter. So first I click on the actual prediction, then I click on model interpreter. And once I click on model interpreter, it's now going to pull up those top 10 features that are influencing the predictions. And you can see these are the values that exist at the moment. This is our target variable. You can see these are the values that were in our predictions. And you can see, starting here, if you wanted to, you could change the value of this feature and see how it may influence your given prediction. You can also look at this next feature, and you can see that no matter the value, it doesn't change your prediction. But here's something that's very interesting. Let's say, for example, we take the CO value and we change it. So you just move it and you click on it. You can dynamically move it. And then once it gets to the value that you would like to move it to, if you want it to stick, you just click on it. But now let's scroll up and we can begin to see how it may influence other particular features. You can see now how it influences this particular feature, where previously before it was flat. Now that we've changed that individual value, we can see that now it's having an effect on the other features. And another thing that you can do, so in this particular case, I'll go back and I'll click back to 2.1. So I'll bring it back to its original value. If I want, I can come to the threshold value and I can say, okay, if I wanted to achieve or identify what are the circumstances that would reach this particular value. So what would need to happen in order to reach a value of 30? Now you can see how each feature would subsequently change, or the range in which it would need to change in order to accomplish a particular value. So you can use this tool to also begin to, if you like, depending upon your use case, identify different profiles that may fit an individual condition. So we allow for you to make these changes on the fly dynamically, not only giving you a significant amount of insight to your predictions, but also helping you to identify what is the scenario or what are the values that need to occur in order to meet a particular scenario. So this is a tool that we're extremely excited about. You can, of course, you can export the feature list if you like, and you have the opportunity to go through and you can do this once again on a prediction by prediction basis. Now we make this available for all of, let's say, web predictions. And of course, if you wanted to also apply this outside of the web predictions, then there's a way that we can certainly instruct you on how you can do that as well. And so next, what I want to do is I want to introduce you to the next tool that we make available in our explainability office. And this particular tool, it's a very long word. It's what we call our model to data relevance indicator. So I'll go back to the prediction tab and hopefully you guys can see the prediction tab. And when you come to this prediction tab, one of the things that you'll see is this dashboard. And this is a new project that we've created. And you can see here, it says 99%. And you can also see this nice little Socrates tree where we have some colorful leaves. Well, one of the things that we make available is that as your model begins to experience decay, or said differently, as we begin to see that your model is seeing data that is different than what you use to complete training, basically this percentage will go down. Maybe the leaves on the tree will begin to turn colors. So to go from what you see at the moment to yellow, you'll also begin to see that the leaves on the tree may begin to fall off. This will be your indicator that maybe your model is decaying, or that it is decaying, and that you need to then subsequently retrain your model. So this is something that is a tool that, of course, our existing customers are finding extremely valuable, and that we certainly believe that you will find valuable as well, is that have that foresight to proactively identify when you need to retrain your model along the way. So what I like to do at this time is just kind of take a quick step back. In summary, I know that our session is supposed to be about 15 minutes, but I just want to highlight and bring back, if I can, my presentation.
Blair, you can go ahead. It's the last presentation of the day, so going over the time, it's not really a problem.
Okay, all right, no problem. Thank you, Theo. So I like to just kind of step back and kind of begin in summary to talk about what we believe is extremely critical when it comes to now managing and implementing your models in production, right? And so we offer this explainability office that we believe is definitely forward thinking. And I encourage all of you guys to, as you look at implementing your use cases, implementing your solutions, ask yourself if the tools that you're using can help you understand and help you answer these 4 W's. Number one, what does your data consist of, right? So starting out, what data do I have? Number 2, which features are important to my model? Which features are not important to your model, right? You don't want to waste time building models with data that actually have no influence on the predictions that you're actually running. And then number 3 is why. Why does your model make certain predictions? And can you validate it? Can you have the insight to know why your model is actually making those particular predictions? And we solve that with our model interpreter. And then lastly, when should I begin to consider retraining your model, right? So you don't want to be in a position where you're reactive and you're getting predictions and you have an erroneous results, whether it's from a technical perspective or whether it's from a business perspective. So this is one of the things that we've provided. It's our model to data relevance indicator, which begins to provide you insight as to when you should take that next step to retrain your model. So these are the areas that we ask that all of you guys keep in mind, especially when you're evaluating the tools that will take you into that next step. So as I begin to wrap up, I again want to thank all of you guys. And I just want to highlight just a couple of more different things. Our objective at Newton is number 1, to make machine learning, tinyML available to everyone. And we believe that we accomplish this by providing a solution that enables data scientists as well as enables the non-data scientists to be able to produce a model. But more importantly, produce a model that is to your business requirements, to your technical requirements, without compromising accuracy along the way. And produce that model in 1 iteration. So very efficient from a labor perspective. And then next, once you reach that point of production, do you have a tool that gives you the insight so that you have the trust and reliability in the models that you implemented in your ecosystem? So we encourage all of you guys to, as we say, build fast, build once, and don't compromise anything along the way. So with that said, I'd like to again extend my thanks to you, Theo, to allow for me to present this session. And of course, thanks to the audience for joining me in this particular session. And I think we'll have the opportunity to have a Q&A coming up where we can go into much more depth, whether it's some questions that were from the keynote or whether with the explainability office. So with that, I extend my thanks to everyone.
Thank you, Blair. It was again pretty remarkable and very good question. So Christoph is asking whether the tool, whether it can be customized with custom metrics, and how are the Borten values chosen in the feature prediction tool?
So let's start, I guess, with the first one. Can the tool be customized? So Neuton is it's an AutoML solution. It is a algorithm that we've developed in-house. We do offer some functions and features that can be enabled and disabled, but again, it's an AutoML solution, so the ability to customize is fairly limited. But under any circumstance, we believe that we are producing a solution that doesn't require a lot of customization once the model is produced. And then I believe the second part of the question is
about the border values.
Yeah, so I believe you may be referring to the model interpreter, if I'm not mistaken. So those border values are coming basically, so the model interpreter is when we actually perform a prediction, right? So those border values are coming from the result of the prediction. And then as you dynamically change the values of those existing features, and then that's what is defining or creating those border values.
Okay. Adrian is stating that he works in education and it's a great platform tool. So I'm going to assume that education is one of the opportunities, the areas that can definitely benefit most from the tool. So Blair, let me ask you a question. Based on your inside experience, does the algorithm always build the most compact models? Does it happen maybe that the models turn out to be the same or even larger than if they were being built with a standard approach?
Yeah, so we definitely out the gate will always build the most optimal model. So one of the things that I've highlighted, or at least I attempted to highlight earlier today during the keynote, is that our definition of an iteration is when we add a neuron. So
Correct.
each neuron that we add is what we consider to be an iteration. And so after we add each neuron in each iteration, we then basically perform some cross-validation against that model at the time. Coupled with an overfitting control mechanism that we've developed internally, that's what allows us to be really confident that the model that we produced is the most efficient model, both from size as well as an accuracy perspective. And Theo, if I'm not mistaken, just so that as more questions occur and we can be as thorough or as deep as we need to, I believe I believe Daniil will be joining me in the Q&A session, so he may step in and answer some of the questions.
He's already asking.
Okay.
Answering quite a few questions as well.
Okay,
Yeah.
all right. Yeah, I just wanted to highlight, just in case verbally he also steps in and asks any questions.
So are you working with some specific set of sensors that generate the data for training and prediction?
I'll kind of give two answers. At this time, when we build models, we don't build models specifically to a given microcontroller or device, right? Okay. So, I understand that there are some tools that are out there that are, maybe a little bit more catered to some physical devices than others. That's not our approach. The models that we produce can indeed integrate really with any microcontroller. Certainly, as we continue to mature and become more and more involved in the tinyML community, we certainly would be looking to collaborate with some partners that are out there. But it's not in our current mandate that we're building anything specific to microcontrollers, to any specific microcontroller, I would say at this time, or any specific hardware device.
Yeah. Well, then leads me to the very next question I was going to ask. A lot of the tiny, if we can call them microcontrollers, are actually 8-bit and below. So I'm going to assume, are you guys supporting 8-bit microcontrollers or smaller resolution, I guess?
Yeah, absolutely. So we support 32, we support 16, and in the demo that we showed today, it was 8-bit.
Oh, okay.
So yes, definitely.
Perfect. And I'm going to assume that you also guys support float calculations, floating point, that is?
Yeah, floats as well as integers. That's correct.
Okay. I really do not like monopolizing the discussion. So I'm looking at the Q&A, but I don't see any questions from the audience. If you have any questions, I don't know if the panelists have any questions as well. But I'm monitoring the box, and in the interest of the discussion, so
So,
I will be.
Tio, I have one, Evgeny here.
Oh, yeah.
So again, great discussion on the explainability of Blair. Thank you. So one question actually I had also in the morning. So your tool and other similar AutoML tools, they're going to change the way people do tinyML and machine learning in general. So in the future, what do you think is going to be more important? The tools like what you're developing or the data? Like who is going to be the king, the data scientist or the software guy who's going to be developing this type of tools?
Yeah, I mean, quite honestly, I think you may be addressing two separate points. So both let's say the software developer as well as the data scientist, when it comes to tinyML, I mean, they're going to remain symbiotic to some degree. And then I think there's another aspect of your question when we talk about, how can we accelerate the growth of tinyML? I mean, the reality, I think, I'm sure you very well know, is that there's a limited amount of resources and capital that companies and organizations are working with. So even if you are a mature organization, you may not necessarily have that data scientist at your disposal, or you may not necessarily have the capital to be able to onboard a data scientist. So I think that in general, those two disciplines will remain symbiotic. But I think when it comes to accelerating or proliferating tinyML, I think that a tool, in this particular case, of course, Neuton, will be key in helping to accelerate the adoption and implementation of tinyML, I think, moving forward.
Evgeny?
Yeah, no, I think thank you, Blair. And another question I had from the morning was more related to your roadmap. I think you showed doing cardio now and then audio in 2021 and then video in 2022. Could you elaborate a little bit more on the roadmap and kind of what features customers and people like developers can expect specifically? What kind of networks they may be able, what kind of workloads they may be able to run in this 21, 22. I mean, 22 is basically tomorrow, right? So just kind of have a little bit of a preview.
Yeah. One of the things I can say, our motto is build fast, but I can tell you that internally we're running fast to begin to apply and add some of these additional features that we discussed today. Right now, I mean, we obviously kind of, let's just say, kind of started in our wheelhouse, you might say, right? So, we've historically had this platform, being able to leverage sensory or tabular data, and we really kind of wanted to really solidify our space in that area. And then I think that we'll continue to add some of the functions that we have on the platform. I think we'll also begin to make some of those functions and features available outside of the platform to, let's say, to be available on the sensor. So as an example of this would be, let's say, the model to data relevance indicator. Right now, you kind of really need to run those predictions from a web perspective to understand when your model may be degrading. And one of the things that we'll certainly be looking at is how can we make this available outside of the cloud, right? Because we from a tinyML perspective, we want everything to run outside of the cloud, right? So there are some of those functions and features that live on our existing platform that we'll also be looking to export outside of our platform. And so that'll be something else that we'll be looking to add to our roadmap, is how we export some of those functions and make them available externally as well.
Okay, this is great. And Tio, it looks like I'm monopolizing the stage here. I have one more question, which is kind of more strategic.
I see Dominic has joined, but yeah, please, Evgeny, go ahead and then
Dominic can ask. This is the last one, Dominic, I promise. So you mentioned cloud and dependency on the cloud. To what extent we tinyML people can believe that at some point we'll have zero dependency on the cloud? Is it possible to think about this at all, or it's kind of a little bit too much? We always need to have a little bit of the cloud to have your system working completely and producing good results?
Yeah, I mean, I think that, and I'm sure this will resonate with you. I mean, 10, 15 years ago, it was data center, right? Make just, and then it went from data center to cloud, right? And then from cloud to edge. And I think we'll continue to see the commoditization of hardware is just a natural progression of technology, you might say. And so as we continue to see microcontrollers become more efficient, have more capacity with a smaller footprint, then we'll be in a position to increase the amount of compute that is taking place literally at the edge. And this is where I was kind of hinting as to exporting some of the functionality that exists now in our cloud to the edge, where those functions can efficiently run on an edge device instead of also in the cloud. So I certainly think that we're going to continue to see hardware become more and more efficient, more and more commoditized, and we're subsequently going to see more and more intelligence be incorporated in those devices. So this is where, again, where you asked before, you have the software side, you have the hardware side, you have the data scientists. And I think those relationships will remain symbiotic because just the dependency between really all three disciplines, I think they'll continue to stick with us for some time.
Thank you, Blair. I think Dominic.
Yeah, so my question relates to iteration. So you talk about adding a neuron by a neuron at each iteration, and I just wonder, can you say anything about how long that iteration takes? Because obviously it depends. Well, it strikes me it must depend a little bit on how much data you're feeding into each iteration. So can you give some kind of indication of the scale at which, sort of like, so I don't know, 1,000 points, 10,000 points, 1 million points, 10 million points, and so on that each iteration takes?
I mean, each iteration is not very time consuming, actually. And this is something that, I mean, we didn't have an opportunity to really demonstrate that today, but we can handle extremely large data sets, and we're still able to efficiently build models fairly quickly, oftentimes in minutes and hours. I mean, of course, a lot of that has to do with the hardware that we're using from a GPU perspective, but the consumption of time in order to go through that process is not very time consuming at all. So there's no trade-off that we've experienced thus far in building models on a neuron by neuron approach. So as an example, it's not taking us longer to build these models. And in fact, we are actually building them fairly quickly by taking this approach, because the way that our algorithm works is, we're excluding information from the onset that we believe to be not important to the predictive power of the model. So it's not extending our building process or our training process, if that's what you're asking.
Not quite. I think my question was, supposing, I mean, some of the data sets are pretty big, right? When you get into image and video, you're going to have big data, as opposed to perhaps for some of the things that you were showing. And having, say, 100 million data points per iteration would be quite small for video, for example. And so my question, I think, is, are you saying that doesn't affect the time the iteration takes, the number of data points?
Dominic, if I may step in, I see Daniel. I don't know if Blair or Daniel would like to answer the question. I saw Daniel asking permission to speak earlier.
Go ahead, Daniel.
Daniel, we cannot hear you, unfortunately. I don't know.
Let's give him a second.
Okay.
Okay, what about now?
Yep.
Perfect.
Yeah.
Okay, yeah.
Okay, it was on my earphones. Great question, Dominic. And I would just like to add a little bit to what Blair has mentioned. So there are 4 key factors on determining how long the iteration will take. So number of features is 1. Then certainly a number of important features is 2, because as you might have seen on the presentation, it's not a fully connected network. It can connect to 3 points or 3,000 points. And that is going to comprise the calculation. Then the number of outputs. Say you have a binary classification problem or a regression problem, or you have a 150 classes multi-class classification problem. That's another constraint. And of course, the number of, say, GPUs. If you're using 1 or 8, what kind of GPU? It's a great question. We did not do that precise calculation of how much time it's going to take for an iteration because it is really always very different. But on the platform, you can clearly see live because the metrics update in real time, and every update of the metrics is 1 iteration. And for the small data sets, small data sets, I mean something with a size of say 10 megabytes, you can see these updates every 5, 10, 20 seconds. And for larger data sets, it can take up to 10 to 20 minutes on the later point of training when you have more nodes in the network.
Sure. Yeah. Okay.
But the first iteration always takes about maybe up to 2 to 3 minutes.
Okay, thank you.
Thank you, Dominic, and thanks, Daniel. There is one new question in the Q&A asked by Rajiv Rajan. What would be an ideal edge hardware device for you to ensure edge intelligence? For example, for 50K neurons under less than 100 microwatts, sorry. I don't know if Daniel or Blair would like to.
50K neurons, 50,000 neurons. Is that what you're saying? We have never had.
That's what it reads in the question. Yes.
Hi, Rahiv. That's well, we've been running thousands of different benchmarks on very large and small and different data sets, and never we have reached the point of 50,000 coefficients in the network. Newton never builds models of that size. It is always going to be, well, I believe in 99% of cases, from my past experience, is something that can fit into a microcontroller. It's always going to be like under 1 kilobyte or maybe under 5 kilobytes at most. So 50,000 weights is something I have never seen with Newton.
Yeah, I'm not sure if Rajiv meant 50,000 neurons or something. Maybe that could be a typo. I don't know. So
yeah, go ahead.
Please. Oh, yeah. I'm looking at the Q&A and I don't see. So we're approaching the end of the session, even if there are any questions. So let me take the opportunity to ask you guys one a little bit more broad question. What are the type of people in terms of companies or activities that you would like to collaborate or looking to collaborate with based on what you've just presented today? So what would be your ideal collaborators in such a scenario?
Yeah, I'll touch on this one.
Thanks, sir.
I'll kind of maybe circle a little bit back to Jenny's question. So I think those 3 areas or those 3 disciplines are going to continue to be at the hip. So when you look at hardware providers of the various controllers, as they continue to become optimized, I think we'll continue to look to expand our relationship with the various hardware providers that are out there, because I certainly believe that even though our models are not being built for a specific hardware device, I think that relationship will continue to be close between, let's just say, the data science community and the hardware provider, right? It's just a natural progression. And then the same thing on the software side. So, we kind of view and see ourselves as really that link between the two. So we'll continue to look to collaborate and to some degree work on both sides of the aisle.
Perfect. Thanks, Blair. I don't see any questions, and maybe I would like to ask you if you don't mind to maybe share some closing remarks with us, or if there's anything that you would like to provide further for us. I think there's around 120 people still watching this, so it looks to be very interesting scenario. So.
There is another question from Rudy, if you don't mind.
Oh, I just saw it right now. Thank you, Daniel. So do you use models like long short-term memory, recurring neural networks, or transformer models for time series data?
Short answer, no. There is no, well, first of all, no open source in our solution. Secondly, our approach is very different from all these traditional neural networks. And of course, you cannot underestimate the power of, say, of LSTM for time series data, but we do this differently. At the end of all the pre-processing and data preparation, we always use Neuton as a final algorithm. Only for the time series types of problems, it's just a different method of Neuton class.
Okay, thank you, Daniel. Yeah, I missed the question. My apologies to Rudy. Thanks to Daniel for spotting it. So let me return back and say if you guys would like to share any concluding remarks, maybe give a couple of more minutes in case anybody has any more questions. There is one that just came up from Evgeny Boltunov. Super interesting presentation, indeed. So did you try to implement a generated model or any kind of FPGAs using high-level synthesis, maybe?
Okay, I can see this. Well, again, short answer is no. You see, we've started this whole project situated around this R&D we've had quite a few years ago, where we have created this algorithm. And we've never even looked into the area of the approaches that are being widely used right now. We started to grow on what we have developed internally. And again, for all the problem types, and this is quite frankly very surprising because, well, as a data scientist, you might use like a linear regression for, say, some types of problems that could outperform, say, XGBoost in some cases. And every time you have to try different ones, then once you select one, you start tuning and so forth. And comparing that to the performance of Neuton, this algorithm constantly, just this single algorithm outperforms all of those, well, according to all the benchmarks that we have made. So it is always Neuton.
Okay. And Adrian is asking, well, it's actually stating that this would be a great for targeting healthcare. Obviously, we saw that in the keynote by Blair with the cardiac monitoring demo. There is a question on the pricing. Daniel, I'm going to let you answer that because I think it's more details that Peter is asking. So if you want, you can maybe answer it in the chat as well. And if I'm looking, let me just make sure we've answered all the questions. We have answered the customization part. We have answered the edge intelligence question, the FPGA. There is another question by Rajiv. Any thought or any comment about hardware based on a reconfigurable spiking neural network?
Excuse me, I'm sorry, I've missed it. Trying to answer the pricing question. Could you please
so Rajiv is asking whether you have any thoughts or any comments about hardware based on reconfigurable spiking neural networks, I'm going to assume.
I'm not sure if I understand this correctly. Reconfigurable.
I think, I'm not sure. Yeah, I'm not sure if I understand it right. Rajiv, if you can please retype your question. And I'm going to go to the next question by David Rogers. David is asking whether there are any publicly available papers or whether you have published any papers that describe your algorithm or your approach.
I'm going to answer the question of David. Well, with the following. we haven't yet published a white paper because, well, this is, well, the basis for our commercial product, but having patented it, we started to explain it step by step. And well, this is one of the first steps that we're taking today. We have some information on our website, and there was an article from ZDNet from yesterday, and there were a few more. And then there was one in Forbes a few months ago. I will send you all these links in a few minutes, but of course, we're thinking about disclosing some details of the algorithm since.
Okay.
Tio, maybe I have a suggestion for Daniel. I saw that Daniel answered quite a few questions during the keynote while we are kind of doing this. So Daniel, maybe you could summarize like some of those questions, the most interesting ones, like what people ask and how you answer them, maybe like the 3 top questions in your opinion. So because this will be a kind of a different audience and this will go on YouTube as well.
Well, there were lots of questions about comparing us to the other neural network frameworks and non-neural algorithms, which is, well, we get that a lot. And well, we've got all those benchmarks which show you the comparison of Neuton against all these other algorithms on the website. But from myself, I would like to say that you can compare in 2 directions. Well, certainly in the terms of performance, and which is very relevant for our today's meeting, in the terms of size. So in terms of performance, we are always performing on the level or better than the traditional and neural network algorithms that we have tested on, and we've tried PyTorch, TensorFlow, we've tried network architecture search with Keras, and we've had network architecture search made by our data scientists. None of them appear to outperform Neuton. And as for the traditional algorithms, well, we've tried all the linear models, all types of boosting algorithms, all types of tree-based models as well, like a decision tree or random forest. We've tried some advanced linear models like support vector machines, and again, none of them really outperform Neuton. And in terms of size, well, comparing to neural networks, it is a big difference, but it is much smaller than the difference between Neuton and, say, tree-based algorithms. I'll give you an example. We've had one project with this one big telecom company from Europe, and the task was to make a prediction with an error of 47 to the -6th power. And we've trained 2 models. One of them was with Neuton, and the other one was with random forest. And Neuton size was, this was a big data set. It was 4 or 5 kilobytes, and random forest model, after having trained for 3 days, was over 10 gigabytes in size with similar performance. So the comparison is quite interesting. I suggest you give it a try and just see for yourself.
Thanks, Daniel. I'm trying to decipher. I asked Rajiv if he can please clarify his question, but I think the way I'm reading is whether you have any comments about the hardware implementing a reconfigurable spiking neural network. But by reconfigurable, I'm not sure if he means dynamic or something else. I don't know if you would like to take a shot at it.
Well, I guess we can maybe connect with Rajiv in private and discuss this question, because I don't know how to comment, because I really don't understand the question at this point.
Okay. Any other questions? I don't see any questions from the audience. Any questions from the panelists? Okay. Well, let me give the microphone to Blair for one more time in case he would like to add anything concluding or any other information.
I guess I'll just like to end by, again, extending our thanks to you, Theo, especially
my pleasure, my honor, actually,
for hosting this session, as well as really the community. We're really excited to be able to be a part of, this ecosystem. I think it aligns really nicely with what our overall objective is, which is to really help proliferate machine learning and tinyML really globally, right? So our missions, I think, align almost perfectly. So just again, thanks. And we certainly appreciate everyone, all of the questions, all of the attendees. And we, of course, we encourage everyone to use our platform, challenge our findings, et cetera. And we look forward to having an opportunity to, collaborate with partners, enable customers, et cetera. Because we certainly believe that, what we're doing at the moment is really, really shifting how, machine learning and tinyML will continue to be approached, right? So I guess I'll just end. I won't go very long and say, thanks again. And we look for the opportunity to partner and work with really everyone in the community.
Thank you very much, Blair. And I was about to ask, there was a comment on the chat about who should Adrian reach out, and apparently Andrew already answered. So thank you, Andrew. Thank you, Blair. Thank you, everybody. Let me, this would not be made possible without our sponsors, whom I would like to once again express our gratitude, starting by premier sponsor Neuton.ai. Thank you guys so much. The executive sponsors, which involve ARM, Edge Impulse, Qualcomm AI, and Sentient. The platinum sponsors, which involve Infineon, Reality AI. The gold sponsors, which involved Latent AI, SenseML. And last but not least, our silver sponsors, which involve EMSA, Greenwaves, Kixo, Imagimob, HOTC, Seed Studio, and ST Microelectronics. Thank you, everybody. See you all tomorrow with more exciting features.